Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Nada El-Falou. I'm a PhD student here at the University of Waterloo, but though I spent most of my time at Perimeter Institute, where my primary advisor is at, so I'm kind of a fake student that doesn't know my way around campus, to be honest. I did my undergrad at the University of Toronto. I double majored in computer science and astronomy, and then I came here for a master's. After completing a year, I transferred to the PhD program, which is considered fast track, and if anyone's considering that, talk to me because there are some things I did not expect going into it. Before I get started on my presentation, I just wanted to say, because I just can't not say, those verses that were read in the beginning were some of my favorites. I just did a presentation for children a couple of weeks ago on verses in the Quran related to space and cosmology. And subhanAllah, there were things that I did not know before. One of them that I can't help but mention is that some verses in the Quran specifically mention the creation of al-ard, the earth, before as-samawat, before the skies. And the Muslim scholar that interpreted that said this is because of the creation of all elemental particles in the Big Bang before the creation, before they formed heavier atoms like the hydrogen and so on, and before they formed stars and galaxies and so on. So I found that very interesting. I just wanted to share that quickly. So my project today, okay. My project is called The Proper Motions from the DESI Legacy Imaging Survey. This is a very technical project, and so I'm gonna try my very best to keep it to focus on the quality and not the quantities, because the units are all very different from what everyone is familiar with, the names of the properties and so on. So I really just want to focus on what I do, not really how I do it. So first I'm going to talk about what proper motions are and why we care about them. And then I'll cover a little about the different instruments, the different telescopes that we use. And then these three here, the DCR, CCD, specific corrections, and the lateral color are the systematic errors that I correct for. And finally, I'll just talk a bit about the summary. So what are proper motions? It's simply the apparent motion of a star in the sky. And when I say apparent, that means the star could be moving in a totally different direction because we're only taking into consideration the 2D motion that it's going through. So we only look at kind of like up, down, right, left, but a star could also be moving towards or away from us. And we don't usually consider that when we talk about proper motions. Proper motions are simply the angular motion of the star in the sky. And so in this diagram, we have it relative to the sun because Earth does move around the sun, so it's better to center around the sun. And you'll see the mu is the proper motion, so that's the angular motion. And the radial velocity in red is what we do not take into consideration because it's the apparent motion in the sky, not taking into consideration the motion away and towards us. Why we care about them? I cannot go into enough details. It would take a whole talk to really talk about why we care about proper motions. But as a general rule, they help us create a 3D map of our galaxy, of the Milky Way, not just of the positions of the stars, but how they move and how they interact. And this tells us about, for example, stellar dynamics, how they interact with each other, how they're affected, how the gravity of the center of the Milky Way affects the motions of these stars, and so on. Similar with evolution of stars, but more than that, galactic evolution, how our Milky Way formed, and that tells us about how other galaxies form as well. And so on. Here I also included finding tidal tails, which are stellar streams. So if you have a cluster of stars within a galaxy, you can have tidal streams of stars that are stripped out from it. So you end up with streams that are leading and tailing the cluster in its movement around the galaxy. And those tidal tails tell us a whole lot about our own galaxy, but they also tell us a whole lot about surrounding dwarf galaxies as well. So there's just so much that we can do with simply knowing where their stars are going and where they came from. What are the DESI legacy imaging surveys that I'm using to create this catalog of proper motions? So DESI is the dark energy spectroscopic instrument. It's a totally different instrument that does spectroscopy. And I'm not going to go into what that is because it's not relevant for today. The legacy imaging surveys are imaging surveys that help us choose targets for DESI. So the legacy surveys are kind of an in-between instrument, in-between data that their primary goal is to choose targets for DESI, but we recognize that, hey, this is really valuable data, and we could do something with it. We could find the proper motions of stars. We have the data anyway. This is practically like free results. So the legacy data is made up of three surveys. There's a dark energy camera legacy survey, the Beijing Arizona Sky Survey, and the Mayal Z-band legacy survey. The other two surveys have kind of lagged behind. The dark energy legacy survey is the one that I focus on because it's the one that has multiple iterations of. So that's the one, when I say I use legacy survey, I really mean the dark energy camera legacy survey. This is the footprint of the survey in the sky. So this is kind of like a projection of our sky. And you can see dark energy camera legacy survey here and here. Can you guys see my mouse? Okay, you can't see my mouse. So the decals are the footprints or like the areas of the sky where this instrument is able to look at. These are just some fun pictures. In my first year, I was very fortunate enough to go to one of these telescopes. The dark energy camera sits on a telescope on a mountain in Chile, in South America. So down there on the left is actually the telescope. On the right up there is a totally different telescope on the neighboring mountain that we just visited because it was cool. And my favorite part of the whole trip was not the telescopes, it was actually the mountain view. It was absolutely beautiful, subhanAllah. So, I just want to talk a bit about Gaia, because Gaia is kind of my motivation for doing this project. Gaia is a space telescope that actually took similar data of stars. So it found the positions and the proper motions of millions of stars in the Milky Way. Again, it's a space telescope, so it's actually outside of Earth and just orbiting in space. And I really use Gaia as ground truth for my catalog, for the creation of my catalog. Gaia has been absolutely revolutionary in this field just by having Gaia data. There has been so much science done on, and still being done in the field. But I want you to notice on point number 1, 2, 3, 4 in Gaia, Gaia can only see up to 21 megs. Magnitudes are kind of a measurement of brightness of a star. It's a little stupid, but it's the historical significance is that there was at some point a guy looking at the sky and he was like, okay, the brightest star is magnitude 1 and the second brightest is magnitude 2. So higher magnitude is actually fainter stars. So Gaia can see up to 21 megs, and it has been revolutionary. Now, if you notice on the right side, Legacy can see up to 27 megs. So my goal here is not to replace the Gaia data, it's to extend it and to help, because I was one of the researchers who was using Gaia data in my undergrad, And I was not able to do much because of the limitation of which stars Gaia could see. So that's the main motivation of this project. And just to show that the legacy data is pretty good, on the x-axis is the magnitude of the source, the red magnitude technically, because it could have different brightnesses and different colors. And on the y, we have the errors of the measurements. And you can see that in orange, Gaia does, expectedly get worse with fainter stars, but the legacy is not that much worse. It kind of follows the trends that Gaia would have followed as well. So the legacy data is very good, and it's a great candidate for extending the Gaia catalog. All right, so here's the overall process. There's the sky. The dark energy camera takes a picture of it, and then we go through the community pipeline and legacy pipe, and those do some really low level corrections, like very specific to the dark energy camera, such that if you just had the raw data, it would be useless. So that's what the community pipeline does. It's by the people who made DECAM itself. And then there is the systematic corrections where I come in, because it turns out that the proper motions I would have gotten if I had just used the data as is are not that great. So I decided to do some systematic corrections first. That's where most of my time went. And then finally, in the last step, I find the proper motions of the stars. Finding the proper motions, by the way, is not rocket science. You have multiple images at different times, and you simply draw a straight line and you say, oh, that's the motion of the star. So that wasn't complicated. The complicated part was actually getting good proper motions by fixing some systematic errors first. So actually, I'll skip that and just go straight into the first systematic error that I corrected for, which we call differential chromatic refraction. Differential chromatic refraction is a refraction of light due to our atmosphere. So if your telescope is looking at a star straight up, then the angle is 0 and the light is not refracted at all by the atmosphere. However, if your telescope is at an angle and looking at a star somewhere there, then the light will get refracted as it's traveling through the atmosphere before it reaches you. On top of that, different wavelengths, as we know from rainbow, refract at different angles as well. And so differential chromatic refraction is that refraction that is due to the atmosphere. This plot here, on the x, you can say this is somewhat the angle or related to the angle away from zenith. So air mass 1 is straight up, and then as it increases, you're going down. And then the relative G minus I color is the color of the star. Again, I don't really want to get into the technicalities of this, so this is not very relevant. What I really want you to know is that there is a trend of the data being incorrect, and it's correlated with the air mass and the color. And this is exactly what I expect, because I know that DCR has an effect on the data. So the color in the plot, the red and the blue, are how off the data is from where I expect it to be according to Gaia. Because I'm treating Gaia as my ground truth, and I'm comparing the stars in legacy to the positions from legacy to that. So I do see this effect. And I know I said I'm extending on Gaia, so I'm actually just doing these analyses and these error corrections and everything on the overlapping stars, and then I apply it to the other stars so that we can actually extend the catalog. So this plot shows, okay, yes, this effect is real, and we can see it. And so thankfully, I don't have to come up with this equation. It's a very simple physical phenomenon, and I won't get into the equation, but I apply the correction, and then after that, I plot again the difference between the Gaia position and my new legacy position, and I say there is no longer a correlation between the how off the position is relative to the air mass and the color, And so I say, oh, okay, yay, I corrected for DCR, and now my data is DCR free. So that was the first systematic error that I corrected for. The second one is very interesting. We call it the CCD tree rings. So as you can see, again, the color here is how off the data, the legacy data is from where we expect it to be according to Gaia. And you see that it creates these very interesting patterns in the CCDs. The CCDs are the charged coupled device. If you're not an electrical engineer, I didn't know this either. They are the little chips in the cameras that actually convert the light into electricity. And so you can see in this specific CCD, there are patterns that look like tree rings, and they are caused by just some very subtle impurities in the CCDs, and it causes the readout to be just a little off. Now, I'm very lucky to have Gaia because I don't even have to model this very complicated phenomenon. I just used my Gaia data. I empirically created the distortion maps, and then I apply these maps to the stars that are not covered by Gaia and correct for their positions as well. And so if I go to the next slide, that is how it was before. And after I apply the corrections, obviously I'm applying the same map, so it's kind of cheating. But the point is that I no longer have the same problem that I had before. Okay. The last systematic correction is this lateral color. So now each of these little rectangles is a CCD, and the whole thing makes up the focal plane of the dark energy camera. And these three plots are binned by color. So I have, let's just call it low color, medium color, and high color in three different plots. And you can see that there is an effect at the edge of the focal plane simply because of the axis symmetric refractive optical system that's in the dark energy camera. Again, no need to go into details about this, but you get the little refraction differences depending on the color in the dark energy camera, and you have these little distortions on the outside. And so I apply, similar to the tree rings, I use the empirical distortion maps that I create from Gaia data. I apply them, and I get rid of this, this effect. All right, so after all that, I look at my error analysis. In purple down there is the theory, if my system was absolutely perfect with no systematic errors, and it was just the only errors I had were because the star was simply too faint to see, it would look at the purple. And we started at the blue. That was where my data used to be. And so with every step, my data got closer and closer to this theoretical error that I could achieve. And I know it doesn't look super impressive in the logarithmic axis, but at the very end there on the left, the blue used to be at an error of 22.6 arc seconds. I'm not gonna get into the details of the units, but 22.6. And then at the red, I took it down to 14.8. So it's a pretty significant improvement, just doesn't look like it in the logarithmic axis. So yeah, I know I ended up at the error analysis. This is because this project is actually still in progress. I am now in the process of running hundreds, if not thousands of gigabytes through my pipeline just to apply all the corrections to the data and actually create the final proper motions catalogs. But that's my project. Thank you.
Okay, we'll open it up to some questions, inshallah. Look up for your vision. If you go back to slide 77.
Oh.
Yeah, the error analysis.
77?
Yeah.
Okay.
Okay, fine. Legacy is supposed to be for the fainter stars. higher magnitude numbers, compared to Gaia, it's supposed to prove the fainter parts of it, right?
Sorry, can you repeat that?
Compared to Gaia, legacy is supposed to prove detecting, fainter stars.
Yeah.
And but here it seems that for the fainter, the stars, you don't need, or I mean, it's already taken care of. The blue is, you don't need much correction for that.
Yeah, to be honest, you're probably right in the, for the most part, but this is very zoomed out. I think I'd have to run a lot more data through to actually see what the effect is at the end there, and I'd have to cut out the rest to see the effect. But hopefully the corrections do improve there as well. And every little bit counts, especially with proper motions.
And at the beginning, you mentioned that Gaia is to your ground truth. I mean, it becomes less reliable as fainter stars, higher magnitudes. But you're applying your corrections based on Gaia as your ground truth. And if what you care about is the fainter stars, and yet Gaia, if your ground truth becomes less reliable, at least what you're blocking to do, how do you account for that? And,
I'm only using Gaia as ground truth up to 20 megs because there's no data beyond 21 megs anyway. So I'm just using Gaia to kind of guide me through the process to analyze my data and so on in the first bit, and then I extend the corrections to the catalog beyond what Gaia can see. So, I mean, for these ones, I'd argue I can't even do much analysis on how much they improve because there's not much to compare them to.
and the assumption is that the same sort of errors present at the lower magnitudes, they will be the same proportion and the same amount at the higher magnitudes.
Yeah. Yeah, because legacy is good at looking at the very faint sources. And so I'd hopefully expect that the correction does well there. Thank you. I think there's a question here.
So far, the data we've looked at, have there been any anomalous patterns or any interesting data points?
There have been. The last time I looked at the data, there were. But as I said, I've been very, very focused on just big data running through the pipeline. So it's been difficult to actually look at results after the analysis. So I'm simply in progress, and I don't have an answer to that yet.
So I'm wondering if you have some sort of gut intuition for what dark matter seems to be according to your project. Does it seem to be QCD axials or something else?
That's not my area of research. The answer I'd give you is what I read in the textbook last week, I don't have any, despite DESI being called the dark energy spectroscopic instrument, and that's not even dark matter, that's dark energy. I have nothing to do with that stuff.
And also to add on to the previous question by James, was there something that really surprised you with your project?
Honestly, not really, because my project is one of the ones that theoretical physicists consider very boring. It's very data oriented, just doing kind of the brunt work of getting the data for someone else to use. So there's not much that is unexpected or very cool. It's more computer sciencey and data analysis than anything. I don't. There's. Thank you.
Any other questions? Okay, let's say thank you again. Oh, you got one more?
I wanted to ask you this one. You do 3 systematic data corrections for the actual for the raw data.
Yeah.
I was curious how you selected these 3 specifically, because I get the differential chromatic fraction.
Yeah.
Why not those include scattering and absorption and things like that?
So scattering is already done by the community pipelines as much as it could be done, because that one needs to be compared to live live weather data, right? Like, you know, just a cloud is passing through and that affects the light and refracts it as it's coming through, and it's just really, I can't remember what the effect is called right now. But that's something that I can't even do because I don't even have that minuscule amount of data. The way I chose my 3 systematic corrections was simply by the biggest ones I could find from previous analyses of the legacy data. They said that these are the 3 biggest ones. So first I did some exploratory work and I was like, yeah, this is a whole arc second of error. So that's how I chose them. But yeah.
Okay, so we got one more.
Did you consider any AI-based filters?
Sorry?
Machine learning filters or image-based machine learning techniques?
I don't think that would work here because there's no way from the image that you can tell where it's going to go, where the data point is coming from. Like, how would you use AI? Like, me as a person, I can't look at it either and tell you, oh, this could be, that's typically how machine learning is used, especially in the image field. You would be like, oh, this is a classification problem or something like that. So not very relevant in this problem. I don't know how much time we have. So.
My question was about why did you decide to correct for the CCD?
So I called it CCD specific corrections just because when I'm using the empirical, when I'm correcting for it empirically, I'm also correcting for some weird, if you saw in the slide. Okay. So see here, there's on the, actually they're not very apparent in this picture, but there are sometimes you can see little screws, like where the screws are, and they also distorted the CCD a little. So that's why I called them CCD specific corrections, but this is actually the tree rings. And similar to my answer to him, it was simply by choosing which systematic errors were causing the biggest fluctuations.
Okay. Thank you again.
All right.
Thank you for